Okay, folks, so welcome to part 3 of my HD44780 LCD tutorial using Mentor Graphics HDL designer software, and we're using the Altera DE2 boards display, and we're driving all the conditions with that using VHDL. So in this part 3 of the video series for this tutorial, in this third video, I'm going to be elaborating on the clock signals and also the infamous 400 Hertz clock signal that was used to drive the LCD core state machine. And I pretty much just skipped over it in the first two videos because I didn't want to overwhelm everyone. But now it's been a bit of over a year now since I've worked on this video series, and a lot of you over the past year, you've been messaging me, harassing me, trying to get me to finally put this together for you, because a lot of you were confused and wanted to understand why this 400 Hertz signal was required and the hexadecimal values that were used in that counter. A lot of you were confused by and just didn't understand why that was required. So I'm going to elaborate on that a little bit, just to explain it so that you understand. Before we move on to that, before we jump into the code, I'll just bring in a shot of the Altera DE2 board here. So the Altera DE2 board's got a 50 megahertz clock crystal on the board, and that's the main source for any counting, and it's the reference clock essentially that's used to drive any processes on the Cyclone II FPGA or any other process that you implement on the board. So with that in mind, let's move into the code now, and I'll bring up the clock process from the code that I had posted on the web page and that was used in videos part 1 and 2. So you can see it here, and because I've actually updated the code, but I'll have both versions of code available for you to reference to. But I've actually gone in and updated the code that I had on the web page with some additional comments just to help clear some questions, and I've also added some different hexadecimal numbers for you to try and use to generate different effects with the LCD display. So I'll just quickly go over the processes now. So with VHDL, just be aware that VHDL is very different from sequential-based programming like C++. So what you have to realize is that keep in mind that processes within VHDL are executed simultaneously. So you can have different lines of code within your VHDL within a process, and all of those commands are executed sequentially. But when if you have multiple processes, well, all of the code that's being executed within each process, those are all being executed simultaneously. So you sort of have, with VHDL, you sort of have both. You have sequential and parallel execution of code happening at the same time. So that's the real difference and advantage for VHDL and Verilog and different hardware description languages used with FPGAs and CPLDs and whatnot. So keep that in mind. So now we'll jump over to the clock here again, and so with the fact that this is constantly cycling, each process will run through all of its code, and then of course when it reaches the end, it starts all over again, and the process is executed over and over and over again at the frequency of the source clock that you use within the parentheses of your process command. So in our case, for the clock signal that we're using to generate this logic high pulse, which the variable we've chosen, we've declared it as clock 400 Hertz enable. But keep in mind that you can name this whatever you want. You don't have to you're not obligated to use the term or the declaration 400 hertz. We just use that because the value that we chose was generating a specific frequency of 400 hertz. Now, the core that was written had that implemented, and I went in and manipulated things around a little bit. And so some of you may have been confused because the frequency that was being monitored, if you were trying to look at this signal that was being used to drive the LCD enable line and create the falling edge for the LCD's enable line, if you were actually probing that with your oscilloscope and trying to see the frequency, pardon me, you probably noticed that it wasn't actually showing up as 400 hertz based on the code that I had posted on the web page initially. And so I think that was what caused a lot of confusion, and a lot of you were like, what's going on? It doesn't make sense. But the reason behind that was that the core that I had used and that I manipulated initially had this 400 hertz declaration, and that was specific to the number of states that were implemented within the state machine of the LCD core. So when you actually add states to the state machine that it's executing, you're actually manipulating the period of the signal on this enable line, and in turn affecting the frequency. So the frequency may not have shown up what it was supposed to be, but so I'll clear that up now, just to explain it a little more in detail so that you know what's going on. So before we move into the code and get into detail here, I just want to take a moment to make a statement regarding the clock 400 hertz enable line here that we're talking about. I think that a lot of you were getting confused with this line, and also getting confused with the actual port for the LCD enable. So be aware that LCD enable is a physical port that's physically connected to the LCD display's enable line for that. And clock 400 hertz enable, this is not these are two completely separate signals. The clock 400 hertz enable line is strictly a clock signal that is used to drive the LCD core state machine. That's it. It's not the same pin as that on the LCD enable for the LCD display. It's not the same pin. So just be aware that the frequency that you're scanning, the frequency that we're actually monitoring with the oscilloscope, is the physical port for LCD enable on the physical pin on the LCD display declared LCD enable. So now I assume that most of you are familiar with the state machine and the concept behind how a state machine works. So I don't want to elaborate too much on that. Otherwise the video might get a bit long. It's already a lengthy video, but essentially you're playing a game of cat and mouse, and you're constantly bouncing around between these possible states that you have, and based on the way that you assign variables and variable names for your control variable for the state machine will determine which state is executed, and all the lines of code that you have within that possible state will have those lines of code executed. So that's the whole purpose behind a state machine, right? So now, with the way that that this was written for this particular process, essentially what's happening is that after every command, after every state that we have that is executed, it will immediately be followed by the drop LCDE state, which is right at the very, very end, which is right here. So the state machine will go through and execute one of our possible conditions that we have. So we have display clear, we have display on, we have mode set. All of these are different conditions. However, the way that we've coded it here is that after it executes this, it will always, as sort of a default, it will jump and execute a drop LCDE before it moves on to the next state in the code sequence. It will always execute a drop LCDE state and all of the code that we have implemented there. So regardless of all of these possible states, by default, after it's done executing that particular state and the lines of code within that state, it will always go and execute a drop LCDE, because in order for that information and the signals to be sent and received successfully to the LCD, of course, we need to have the LCD's enable line go to a logic low state, creating a falling edge. The fact that that's occurring, that's 2 cycles of the state machine. It has to go through it once and exit the state machine for the command that you're running, or the state where you're actually sending information to the data bus. So that means that our 400 hertz clock pulse, or whichever pulse that we would declare to drive the state machine, is activated once. It is pulsed high, and it drives that state once. And then what is it doing there? Well, our signal on our LCD enable is in a logic high state. And then in order to create the falling edge, it has to drive low. So it has to create another signal pulse to have the falling edge created. So from start to finish, our cycle is first high, then it's low. And so if you think about that, the period of this signal has been extended because we're using 2 of these pulses, because we have 2 states. We have the first state, which is our logic that we're sending to the LCD, and then we have to have it immediately followed by the LCD enables falling to a logic low. That's the signal cycle for the LCD enable line. If you think about it, the fact that we have that, it means that our whatever variable that we've assigned to generate this pulse within our clock process, and that variable being the counter variable here, the hexadecimal number 0F424. Now, when you do the math and you process this, that particular hexadecimal value is used to generate an 800 hertz pulse. So now why was 400 hertz chosen when this variable was being used? Why is it half of what this was intended? Well, because the core was designed for us to be using 2 states within the state machine, one for executing the command and then one at the end for the falling edge of the enable line. A lot of you were probably couldn't understand why this clock 400 hertz enable was chosen. That's the exact reason, is because the original core that was implemented was coded to always have 2 states being executed one after the other before the next command would actually be run. So that's why the 400 hertz, it was actually a variable here for 800 hertz. But when you actually monitored the signal with an oscilloscope on the DE2's LCD enable line, it would actually come up as half the frequency, half the set frequency for this variable. Now, a lot of you are probably sitting there saying, "Wait a minute! I hooked up, I used the code that Jerry had put on the web page, and I hooked it up, and I hooked up my oscilloscope to the LCD's enable line." And it didn't show up as 400 hertz. It was different. It was something else. And I'll explain why. And that's because when I was manipulating things around, I added an additional state to the state machine. So we ended up having 3 states being executed one after the other before the next command would run. So that extended the period of that signal. And so with the period being extended, doubled, and then tripled, well, that's each time that's going to divide your frequency down. So that's why a lot of it. So what I ended up doing was, for the last states that I had within the state machine, you can actually move things around and shorten it so that it is in fact only 2 states. And then you will actually get the official 400 hertz as shown here. So it's a bit confusing, I realize, and I hope that I haven't lost you, but if I have, I do apologize. I'll do some samples here. We'll do some examples, pardon me, and we'll run through it. So I'm gonna have this run. This is the exact way with the added hold state that I put in there. This was exactly the way that I had it set up originally with the code that I had in the first 2 videos. So I'm going to compile this code, and we're going to go look at it on the DE2 board, and also monitor the logic enable line on the LCD, and check out and see how that looks and how it reads on the oscilloscope. And then I'll talk about it a little more just to clarify. So let's do that now. Let's move over and program the LCD on the DE2 board. Okay, so I've got the DE2 board booted up with the welcome screen there. I've got the oscilloscope monitoring the LCD's enable line, and I've got Quartus here ready to load the original code that I had posted on the web page. So we're going to program that now, and then we're going to check out the frequency on the enable line, and we'll investigate that. So here I go. So I'm going to program it there now. Let's watch the LCD display. So programming now. Boom, there's the message. So it works out. Now, let's take a look at the oscilloscope here for monitoring the LCD's enable line. So technically, we should have 400 hertz there. But now when you were monitoring it, you were seeing 266 hertz with a period of 3.75 milliseconds. And the duty cycle was actually 33.4. So a lot of you are probably sitting there going, what the heck is going on? This doesn't make any sense. Now the reason for this is because the period is being extended by each of the states within the LCD core, the state machine. So by running 3 states within that state machine, we're manipulating and changing the period, the duty cycle, and the frequency. What I actually ended up doing was going and rectifying this and putting it back to only actually run 2 states as it was originally designed as part of the original LCD core. So a lot of you were sitting there and confused and didn't know what was going on. And so the reason for this was because I had gone in and manipulated it against the original LCD core. And so by removing that hold state that I had added, by removing that, I was able to put it back to its original condition, and the frequency on the LCD enable came up to match the variable name that they had chosen to call that particular clock pulse at 400 hertz. The fact that they chose to call it 400 hertz when technically it was not was kind of it just confused the heck out of everybody. But I know a lot of you were curious as to why it didn't match and why they chose to use the variable name 400 hertz for that particular clock pulse. And so that's the whole mystery behind it, is the manipulation of the state machine and going against the intended signal that they wanted to monitor on the LCD's enable line. So let's move on, and I'm gonna start to use the actual the new code that I've posted on the web page. So we'll compile that with Quartus there down to it, and then we'll be able to see the actual intended frequencies that we declare. and it should show up correctly here on the oscilloscope for that LCD enable line. Okay, so for this one, we're actually going to load the official new improved code, where I've removed that hold state within the state machine. So we've no longer got 3, we're going to actually have 2. And so then that should actually split the official 800 hertz frequency down to 400 hertz. And we should see the 400 hertz here on our screen. So we're going to load the hexadecimal value for the 800 hertz frequency. So let's do that now, and we'll program it in here to the board. So let's watch the screen as I load it. So here we go. So this is for the 800 hertz hexadecimal value. So here we go. Boom. So you can see how quick it was there. So a lot faster. And here on the scope, we've got our 400 hertz, and we've got a period of 2.5 milliseconds with a 50% duty cycle. Okay, so we've got it all loaded here. So I'm going to set it up, and we'll program it, and then we'll take a look at it here on the DE2 board. Okay, so here we go, programming now. And there it's done. And whoa, what's going on? Oh, it's not showing up. Oh, that's interesting, isn't it? So let's take a look at our frequency here. So we've got 800 hertz, which is correct. Our frequency is cut in half. And our period is 1.25 milliseconds at a 50% duty cycle. So now, the question is, why is it not showing up on the screen? Well, by using 1600 hertz signal, chances are we're exceeding the speed of the LCD display, the maximum frequency that this can handle. So when we take a look at the data sheets, chances are that's why the signals aren't able to be grasped. It's at the frequency is too high for it to process it, and so 1600 hertz clock for that enable line is just is too high, which is one of the main reasons why the 400 hertz signal was chose in the past, which is just to bridge that speed requirement for the LCD display. But you can play with it and fine tune it and use your own hexadecimal numbers and try to tweak it to get it at the right spot. But even when we're using the 400 hertz signal, it loads it pretty quickly. Okay, so we're set up and we're ready to load the 10 hertz hexadecimal value for that 400 hertz enable line. So let's program that and let's watch it as it displays that sequence onto the LCD display of the DE2 board. So here we go. So programming now. So there it goes, just finished. Wow, you can see how slow it is. And that's the 5 hertz that's being generated for each of those states. And now my oscilloscope, I'll try the auto scale here. Yeah, and you can see how it's, don't think it's gonna grasp it. Nope. Oh, there it is. Let's see if I can get it here. Carriage it down. Yeah, there it is. So now I'll bring the voltage levels down and I'll center it. Okay, and there it is. So we've got 5 hertz, 200 milliseconds with a 50% duty cycle. So there you go. So that's a pretty slow speed there. Almost almost down to 1 hertz there, or 1 character per second. So let's just watch it again. I want to see that again, so I'll reset it and I'll program it one more time just to watch it again. It's pretty slow. So here it goes. Yep. Okay folks, so that concludes my tutorial for the HD44780 LCD display using Mentor Graphics and HDL Designer with VHDL on the Altera DE2 board. Good luck on your projects, and we'll talk to you guys later. Bye for now.